The Burj Khalifa is 828 meters tall. On a windy day, the top of the building moves over 2 meters from side to side. The people inside feel it. The building was designed to do exactly that. And understanding why movement is the solution rather than the problem changes the way you look at every tall building you have ever seen. Let's start with the fundamental engineering challenge. A tall building is not fighting gravity. Gravity is actually the easy part. The force that tries to destroy skyscrapers is wind. And the taller a building gets, the more devastating wind becomes. Wind force doesn't scale linearly with height. It scales exponentially. A building twice as tall doesn't face twice the wind load. It faces dramatically more. At the height of the Burj Khalifa, wind speeds can reach 150 kilometers per hour, and the lateral force pushing against the building can be measured in hundreds of thousands of tons. The naive solution would be to make the building rigid, build it stiff enough that wind cannot move it. Engineers tried this in the early days of skyscraper construction. It doesn't work. A perfectly rigid structure subjected to extreme wind force doesn't bend. It breaks. The engineering insight that changed everything was counterintuitive. Don't resist the wind. Work with it. The first major tool is the building's shape. The Burj Khalifa's distinctive tapering spiral form is not primarily aesthetic. It is aerodynamic engineering. As the building rises, it gets progressively narrower in a specific pattern. Each setback in the building's profile disrupts the wind's ability to form coherent vortices around the structure. Wind flowing around a tall building naturally creates rotating columns of air called vortices on the downwind side. These vortices shed alternately from each side of the building in a phenomenon called vortex shedding. If the vortices shed at the same frequency as the building's natural resonant frequency, the building begins to oscillate. Each oscillation reinforced by the next shed vortex in a process that can build to structural failure. The Burj Khalifa's spiral taper means the wind never encounters the same cross-section twice as it travels up the building. The vortices form at different heights at different frequencies. They cannot synchronize. They cannot build resonance. The shape of the building defeats the wind's attempt to find a rhythm. The second major tool is the building's internal structure. The Burj Khalifa uses a buttressed core structural system, a central hexagonal concrete core connected to 3 wings by load-bearing walls. The concrete core resists torsion, rotational forces, while the wings resist lateral forces from any wind direction. The entire structure works as a single integrated system rather than as isolated components. The concrete itself is extraordinary. Standard concrete would crack under the thermal stresses of Dubai's climate and the structural loads of a building this size. The Burj Khalifa uses a high-performance concrete mix that was developed specifically for this project, poured only at night during the summer to prevent the extreme heat from causing premature setting that would compromise structural integrity. The concrete was pumped to record heights using specially developed pump systems. At the time of construction, pumping concrete to 600 meters was considered at the boundary of what was physically possible. The steel reinforcement embedded in the concrete is not simply bars running vertically and horizontally. It is a 3-dimensional cage of interlocking elements designed through computer modeling to distribute load paths through the structure so that no single element is ever a critical point of failure. If any one component is overstressed, the load redistributes through adjacent elements. The building has no single catastrophic failure point. But concrete and steel alone don't solve the oscillation problem. When a building of this height begins to sway, even controlled, designed sway, the motion is perceptible to the occupants. Extended exposure to even low-level building movement causes motion sickness, disorientation, and psychological stress in the people inside. The engineering solution to this is one of the most elegant in structural engineering: a tuned mass damper. A tuned mass damper is essentially a massive weight, in some buildings hundreds of tons, suspended inside the building near the top, connected to the structure through a system of hydraulic dampers and springs. The mass is tuned to oscillate at the same frequency as the building, but precisely out of phase. When the building sways in one direction, the mass moves in the opposite direction. The movement of the mass exerts a force on the building that counteracts the sway. The building's motion energy is transferred to the mass and dissipated through the hydraulic dampers as heat. The most famous example is Taipei 101 in Taiwan. Its tuned mass damper is a 660-ton steel sphere suspended between floors 87 and 92, visible to visitors. During Typhoon Soudelor in 2015, the damper moved over 1 meter to counteract the building's wind-induced sway. Wind tunnel testing is a critical part of every super-tall building's design process. Scale models of proposed buildings are tested in wind tunnels with accurate models of the surrounding urban environment. Pressure sensors on the model surface measure the wind loads at every point under different wind speeds and directions. The data from these tests directly informs structural decisions, sometimes requiring changes to the building's shape, orientation, or surface treatment before a single foundation pile is driven. The foundation of a super-tall building is an engineering achievement equal to everything above ground. The Burj Khalifa sits on 192 piles, each 1.5 meters in diameter and 50 meters deep, driven into the ground below the building to reach load-bearing rock. The raft foundation connecting these piles is a continuous concrete slab, 3.7 meters thick, covering the entire building footprint. The total concrete in the foundation alone would fill several hundred Olympic swimming pools. The building's weight is distributed through this foundation system so that the pressure on the ground beneath is within the bearing capacity of the underlying geology. The elevator systems in super-tall buildings are engineering challenges in their own right. The Burj Khalifa has 57 elevators. The longest runs travel from ground level to the observation deck at level 124, a journey of over 500 meters. At these heights, elevator cables become impractically heavy under their own weight. The engineering solution involves sky lobbies, intermediate transfer floors where passengers change elevators. Double-deck elevator cars serve multiple floors per stop. The elevator systems in super-tall buildings represent some of the most complex vertical transportation engineering ever attempted. What makes all of this work together is the computational power available to modern structural engineers. Every super-tall building today is designed using finite element analysis, computational models that divide the building into millions of tiny elements, each with defined material properties, and calculate the stress, strain, and displacement of every element under every conceivable load combination. Wind loads, seismic loads, thermal loads, occupancy loads, construction sequence loads, all modeled simultaneously in 3 dimensions. The computers identify the critical load combinations, the vulnerable structural elements, the potential failure paths. Engineers then modify the design until no single failure path leads to progressive collapse. The result is a building that moves, a building that flexes and sways and responds to the forces acting on it rather than resisting them rigidly. The Burj Khalifa moves 2 meters at the top because the engineers designed it to move 2 meters at the top. That movement is the engineering working exactly as intended, dissipating energy, preventing resonance, keeping a 828-meter structure standing in a city where the wind never stops and the temperature swings 40 degrees between seasons. The tallest building ever built moves because moving is how it stays standing, and the next one will be taller.